This is another exam 4 review video. This one's going to focus on the signs of product of inertia of areas that are at different orientations in the X and Y axes. So depending on the orientation of the shape, the product of inertia for that shape can be 0, can be positive, or can be negative. And this is a common conceptual question on exam 4. And so you need to be clear in your brain on how to identify those signs. And frankly, the signs of the area follows from the definition of product of inertia from the integral of xy dA or from the parallel axis theorem itself. So let's look at some examples of this. So this is a simple example that uses the product of inertia, or that uses the parallel axis theorem for product of inertia. I've created an XY coordinate system, and there's 5 different little dAs. 1, 2, 3, 4, and 5. Recall the parallel axis theorem for product of inertia. So IXY, which is the product of inertia of a given area about the X and Y axes, is equal to I bar of that area the I bar XY of that area about its own centroidal axes plus its area times dx times dy. For all of these areas, these are all basically rectangles or squares because they're symmetric about their centroidal axes. All of their I bars are 0. So the IXY of all 5 of these guys is just equal to their area times dx times dy. So if you build a table for these 5 different areas, they all have the same area A. All of their I bars are 0. The dx and dy's take on different signs depending on the quadrants. And so for this area 1, his dx and dy are 0. If you look at area 2, the dx, which is the distance from the y-axis to the centroid of area 2, is positive. dy, which is measured from the x-axis to the centroid of area 2, that's also positive. So for area 2, dx is positive, dy is positive. So when you take A times dx times dy, then the IXY for area 2 is positive in this quadrant. If you take area 3, his area is A, his dx, which is measured from the y-axis to his centroid, that's a negative dx. The dy here is measured from the x-axis up to 3, so that's a positive dy. And so the A dx dy term for area 3 is negative in this quadrant 2. In quadrant 3, down here, for area 4, the dx is negative, the dy is negative, and so the A dx dy term is actually positive down here in quadrant 3. And then finally for area 5, we have a positive dx, a negative dy, and so his IXY is negative down here. And I note that here, positive, positive, negative, negative, that follow from the dx dy terms. And so basically what that leads us to is if you have a general area that's that has an area in quadrant 1 and an area in quadrant 3, these IXYs are all positive. And so basically any area that extends somewhere along the diagonal from quadrant 1 down to quadrant 3, that's going to be a positive IXY. For this problem, where you've got an area in the quadrant 2 and in quadrant 4, for this guy, you get a negative IXY. I'll let you do the math. And so basically any area that is mostly lies along the diagonal from quadrant 2 to quadrant 4, this guy is going to have a negative IXY. And then, of course, an area that's symmetrical about the y or symmetrical about the x will have a 0 IXY. So remember, IXY is used in our moment of inertia transformation equations, and it's kind of a measure of the skew of our area from its principal orientations to a non-principal orientations. And so remember, IXY for an area that is already at its principal orientation, where its IX is like a max and its IY is a min or vice versa, then the IXY is 0 in that case, if they're principal. So this you need to know. This conceptual idea is often on exam 4. And this is kind of a related problem to that. I call it a many areas problem. Each of these areas, there's like area 1 through 14, all basically have the same area, but they're in different locations in the XY plane. Each area is going to have its own product of inertia relative to the X and Y axes. All of those terms will be the area itself times a dx times a dy. So in general, again, just considering the product of inertia of the individual areas, 3, 4, and 7 up here will all have positive IXYs. All of these guys will have positive IXYs. All of these guys will have negative IXYs. And all of these guys will have negative IXYs because of the signs of the dx and dy terms. 2 will have a 0 IXY because he's centered on the y-axis because his dx is 0. 8 has a 0 product of inertia because his dy is 0. If you combine any combinations of these guys, like 1 and 3, because 3 has a positive IXY and 1 has a negative, then they're going to approximately cancel one another out, but it looks like 3 is closer to the y-axis. They look like they're about similar in the distance from the x-axis. So they'll be, cancel one another a little bit. 6 and 7 are both, 6 is negative, 7 is positive. 7's a little bit larger because it's farther from the y. So the combination of 6 and 7 is going to be slightly more positive than negative because of these guys. 7 and 14, 7 is positive, 14 is negative, but because 14 is farther from the x-axis, he's going to be a larger magnitude than 7. So the combination of 7 and 14 will be slightly negative. So again, any two of these will have a dA between two of them that's, either adding the positive terms or adding the negative terms or the positive and negative canceling one another out. So the absolutely largest positive numbers are going to be like 4 and 13. 7 and 10 will be also positive, but smaller than 4 and 13. The largest negative guys are going to be a combination of like 1 and 4, or maybe 5 and 12. A combination of 6 and 11 will be negative, but smaller than 1 and 14. Again, if you combine 7, which has a positive, plus 8, which has a 0, then that'll be positive. If you combine 11 plus 8, 8 is 0, 11 is negative, so that combination is negative. If you combine 5 and 9, 5 is negative, 9 is positive, but 5 will be larger because he's a little further from the axes, and so the combination of 5 and 9 will be slightly negative. And so that's the kind of thinking that you need to think. You need to think about the IXY of the individual area and then combine the two together to see what the combination of the two would be. And it's just basically the sum of the two. But again, because all of these are symmetric areas, all of their I bars are 0. And so all of their IXYs are just area times dx, dy. The area, the dx's and dy's can be positive or negative. And so the IXYs can be positive, negative, or zero.